Yeah, I hope this is visible and you're able to hear me as well. Once again, students who had registered for SDP on big data, they can actually attend that SDP. Anyhow, the class recording, I will make it available on YouTube. So you can go through that there. Okay. But attendance there is compulsory. I will verify the attendance from the workshop as well. Okay. So I hope I'm audible.
ಸರ್ ಇನ್ನೂ ಲಿಂಕ್ ಕಳಿಸಿಲ್ಲ ಸರ್ SDP ಅಲ್ಲಿ ತನಕ ಇಲ್ಲೇ ಇರೋದಾ ಸರ್?
ಲಿಂಕ್ ಕಳಿಸಿಲ್ವಾ ಇನ್ನೂ ನಿಮಗಾರು?
ಇಲ್ಲ ಸರ್.
Okay, ಆಯ್ತು. But if they send the link, then you can join there. How many of you are registered? Can you raise your hands, please? Okay, students who have registered, if they send a link, then you can join there. Till that you can continue here. Okay, I can lower your hands now. Right. So in our last session, we were discussing about the concept of lexical analysis. We have seen what is the role of lexical analyzer and how it actually works with our syntax analyzer, which is the parser. So this was the interaction that actually takes place between lexer as well as parser. The lexer is supposed to give tokens to the parser, and it will do so only when parser actually asks, right? So you can see that in the diagram, the interaction takes place from the parser. It would actually invoke lexical analyzer by a function called as get next token, which is basically a call to your lexical analyzer. So then the lexical analyzer would actually read the source program, group them into tokens, and then return those tokens back to the parser. Now this is a continuous process as long as the parser requires token for syntax analysis. And this will be over once the source program has terminated or it's the end of the source program. Now throughout this interaction, we had seen that symbol table is also going to be used by both lexical analyzer as well as parser. So tokens are going to be inserted into the symbol table by the lexical analyzer and later verified and used by the parser and other phases of the compiler. Right. We also saw that we can divide our lexical analysis process into two different processes. First one is the scanning, where we basically take out the unwanted things like spaces or comments or white spaces, okay, so on and so forth. And in the second process, or as a second process, we will be keeping track of the program itself, and the process is called as lexical analysis phase, where we divide our source program into sequence of tokens. Right. So why did we choose lexical analysis over parsing, or why didn't we integrate the lexical analysis part in the syntax analyzer itself? There are plenty of reasons for that. One reason being it makes the design simple, and it basically improves the efficiency of the compiler. And third one being it improves the portability of the compiler. So this is one of the reason, along with the other two, that actually makes us consider lexical analysis as a separate part. We also talked about tokens, patterns, and lexemes. What do you mean by each one of them? Basically, a token is something that is written by the lexical analyzer, and it is consisting of a pair with name and an optional attribute value. A pattern is something that or basically is the description of the form that the lexeme is supposed to take. And a lexeme is basically a sequence of character in the source program that matches a particular pattern, right? So we had discussed about this concept. So like for example, for certain things, the pattern remains the same, the lexeme remains the same, but the token that might be returned is keyword. Like for example, if is a token and the lexeme for it is if only. Okay, or the pattern for that is also if, which is basically what we are looking for. Okay, so like this we can basically distinguish between lexeme, token, and pattern. Okay, and when it comes to attributes, normally the attribute would be the pointer to the symbol table in most of the cases, especially for tokens which are variables or identifiers that are used in our program. Other than that, if they are numerical values or if they are operators, then they may not have an associated value. For number, of course, the value itself becomes an attribute. But for other operators, we need not have any attribute value as such. Okay. Like this example we had seen, E is equal to MC square, and the possible set of the tokens that are returned by the lexic analyzer is actually shown here. Okay. When it comes to handling errors, so lexic analyzer can come across errors in the source program, and the type of errors that is handled by the lexer is going to be important, right? Because it basically affects the efficiency of the lexical analyzer. So sometimes when errors are encountered by the lexical analyzer, it actually does something to recover from that particular error. Like one major strategy that is utilized by the lexical analyzer is the panic mode recovery, in which we are going to delete the successive characters, or we are going to skip over the input in such a way that we come across something which we are which actually is known. Okay, so like for example, some lexical unit is actually known. So from there, the lexical analyzer can actually continue. So this is one type of error in which the lexic analyzer actually handles it. And the other possible recovery actions are that they can delete one character from the input, insert a missing character, replace a character, or transpose to adjacent characters. So these are some of the strategies that the lexic analyzer can actually take. So we also talked about the input buffering scheme, where two buffers are actually used of size n, and they are loaded alternatively, which actually saves us the time of reading the source program. So instead of reading the source program one character at a time, now we can actually read the entire source, not the entire source program, of course, at least n bytes of it into our source, into our buffer, and we can continue the lexical analysis. So for example, here a diagram has been shown. So this is the two buffered technique, where one buffer is loaded with the source program by reading the source program through a system call, and other buffer is loaded appropriately whenever needed. We maintain two pointers as mentioned, lexeme begin and forward lexeme begin, which marks the beginning of the lexeme that we are trying to estimate, and forward is basically a pointer that would be advanced to find out the boundary of that particular lexeme. Okay, and every time we advance the forward pointer, we will check whether we have reached the end of the buffer. So if we have reached the end of the buffer, we will load the second buffer and continue. Of course, the program itself can end, in which case we will encounter an EOF at the end. Okay, so this technique can be improved by using the concept of sentinels, which would actually be introduced into the buffer itself at the end, right? For example, each buffers are going to be marked with EOF as shown in the figure here. They will be marked with EOF, and whenever we are advancing the forward pointer, we will check for two things now. One is either the end of the buffer has been reached, which is marked by this EOF, okay, or it may be some other character, or we have reached the end of the file itself. So if you have reached the end of the first buffer, we will load the second buffer. If you have reached the end of the second buffer, we will load the first buffer, and the forward pointer is going to be circled around. So we can write a code for that process which we have discussed so far like this. Like as I said, forward would be advanced, forward plus plus. So whatever character we have come across, it can be either of these things. So either it can be EOF or it can be something else. So if it is EOF, then there are two possibilities. Either we have reached the end of the first buffer or the second buffer, or else we have come across the end of the input itself. So what to do when we come across end of the first buffer? So if forward is at the end of the first buffer, you reload the second buffer, and forward is set to the beginning of the second buffer. Second thing is, if forward is at the end of the second buffer, reload the first buffer and set forward to the beginning of the first buffer. Suppose if it is the end of the file itself, then terminate the lexical analysis, right? So if any other lexemes are found, then obviously write the cases for those characters that has been read. So this is how input buffering technique can enhance the speed of the lexical analysis phase, and that's what makes lexical analysis more efficient than the syntax analysis. If syntax analysis was also supposed to take up the job of lexical analyzer. Okay, so now to talk about some of the ways in which you can specify the token. See, now we are supposed to make sure that our lexical analyzer actually returns us tokens. So how do we specify that this token is supposed to be returned, or how do we specify that this is the lexeme that we are supposed to identify, right? So as mentioned, lexical analyzer basically uses regular expressions. Okay, so it uses regular expressions to specify the lexeme patterns, and using these patterns we are able to determine what token is supposed to be returned by our lexical analyzer. Now for that to happen, we need to understand few concepts that are related with regular expressions. Of course, I think you might be familiar with these things, so it would just be a recap of what you have learned so far. Okay, so let us start by defining certain terminologies under strings and languages. Okay, so what do you mean by a string and what do you mean by a language, right? So for these terminologies to be discussed, we need a few more definitions which we will go through. Okay, so let me share another screen. Okay, I hope this is visible. Okay. Right. So let us start with the alphabet. Right. So let us start with an alphabet. So what do you mean by an alphabet? We are supposed to define string, by the way. So we'll start with what exactly a string is made up of. So an alphabet is a set of symbol, okay, or it's a finite set of symbol. That's the definition of an alphabet. Like English language has around 26 alphabets, right? So binary language has two alphabets, which are 0 and 1. Okay, anything that is binary is made up of only these. ASCII is also one more example for a collection of symbols, okay, ASCII characters, right? So this is what an alphabet actually means. Okay, now using the definition of alphabet, let us define a string. So what do you mean by a string? Okay, I hope this is visible. A string over an alphabet is a finite sequence of symbols drawn from that particular alphabet. Okay, or you can simply put it as it's a finite sequence of symbols. Okay, it's a finite sequence of symbols, or maybe you can also put it as a sequence of alphabets, right, or a collection of alphabets. So that can also be considered as a string, right? So in case of our regular expressions and languages, we can also have an empty string which is epsilon, and every string would have a length associated with it, which is nothing but a number of alphabets that appear in that particular string. And if it is an empty string, then the length of that particular string can also be equal to 0. Okay, so this is about a string. So what's a string? It's a sequence of symbols. It can have a length associated with it. It can also be empty and whose length is 0. Okay, now let us look into the formal definition of what exactly is a language, right? So as you can observe here, a language is any countable set of string over some fixed alphabet. Okay, or you can say that language is basically a collection of strings. Okay, so or as it is defined, language is any countable set of string over some fixed alphabet. Okay, like for example, a binary language, right? So what does a binary language comprises of? So the alphabets are 0 and 1. The alphabets are 0 and 1. Now using these zeros and ones, I can basically make up any string. Okay, like for example, this is a string. Okay, what is the length of this particular string? Length of the string is 5. Similarly, this is also a string. Okay, this is also a string, right? So its length is something else. So this collection, okay, so this collection of string over a set of alphabet becomes a language. Okay, I hope you are getting this. So this is what a language is, right? So language is any countable set of strings, okay, over some fixed alphabet. Okay, so this is the definition of a language, right? Now, when it comes to strings, you have got other terminologies associated with that. There can be different types or different parts of a string. Let us look at each one of them. The first term is called as a prefix. Okay, what's a prefix of a string? So prefix of a string yes. So let us call the string as s. So prefix of a string yes is any string obtained by removing 0 or more symbols from the end of the s. Okay, so it is a string that is obtained by removing 0 or more symbols from the end of the yes, end of the string yes. Okay, so what do you mean by this then? So if I have a string ABC, so what are all the prefix of that particular string? I have a string ABC, then and let us call this as yes. Okay, so if I have this string, then what are all the possible prefixes? So prefix I can get by deleting what, or by removing 0 or more symbols from the end of yes. So 0 or more what? So 0 means I am not removing anything. So this is a prefix of yes. Okay, similarly, if I remove one character from the end, it becomes AB. So this is a prefix of yes. Okay, if I remove two characters, this also becomes a prefix of yes, right? So this is what a prefix is, right? So let us now look at the second definition, which is suffix. Okay, it is exactly the opposite of prefix. So suffix of string yes is any string that is obtained by removing 0 or more symbols from the beginning. Okay, so it's exactly the opposite of a prefix. Okay, now let us look at another definition, which is substring. What's a substring? So substring of s is obtained by deleting any prefix and any suffix from s. Okay, means you can perform the deletion from either side, and whatever remains, that is going to be considered as a substring. Okay, like for example, if I take ABC and if I delete at the end, I will have AB. So AB is a substring. Okay, if I delete from the beginning, I will get BC, which is obviously a suffix, but even this is a substring. Okay, now remember that when I say I can delete from the beginning and the end, does not mean this. Okay, like for example, I cannot delete B and say that AC is a substring of ABC. No. Okay, AC is not a substring of ABC, but AB is, BC is, even B is, right? So, but AC isn't. I cannot delete anything randomly. Okay. Just a second. Okay, so as I was saying, a substring is something that is obtained by deleting either the prefix or the suffix, right? So as I mentioned, for ABC, AB is a substring, BC is a substring, B is a substring, A itself is a substring, C itself is a substring. But AC cannot be a substring, right? So you can't randomly delete characters at the middle and say that it is a substring. Okay, so that is what one thing you need to remember. Okay, next we have proper prefixes, suffixes, and substring. Okay, so what do you mean by a proper prefix? So proper prefix and suffix and substring of a string S are those prefixes, suffixes, and substrings respectively of S that are not epsilon or not equal to S itself. Okay, what do you mean by this? Like for example, if ABC is a string, okay, if ABC is a string, then what is a proper prefix and proper suffix? Anything that is not empty, okay, or anything that is not equal to yes. Okay, so all of these things can be considered as a proper suffix or proper prefix and substring. Okay, like for example, ABC itself is not a proper suffix or a prefix or a substring. Okay, but AB is a proper prefix. A is a proper prefix. Similarly, BC is a proper suffix. C is a proper suffix. Okay, all of these, whatever I have mentioned, they are including B now, is a substring. Got it? So this is what proper suffix, proper prefix, and proper substrings are. Okay. Then comes a subsequence of S. So subsequence of S is found by deleting 0 or more, not necessarily consecutive position of yes. Okay. So this is what I was talking about. So when you delete things randomly, it becomes a subsequence, not a substring, right? So this is one more example, right? Now that we are talking about language, so a language can be formed by concatenation of different strings. Okay, so all those rules we are going to look into anyhow. But now let us look into some of the operations on the languages, right? So we have seen the basics definitions. So now we shall look into what operations are supported on languages, right? So normally following operations are supported, as you can observe. First one is the union of two languages. If I say L and M are the two languages, then L union M will basically contain, okay, set of strings that are present in both L as well as M. Okay, I believe you are familiar with these concepts. Then concatenation, which is indicated with LM, will contain strings, okay, where S is in L and T is in M. Okay, so you put together both of them. Then there is a clean closure, which is one of the operation which we are familiar with somehow, which is called as L star, where it basically is nothing but zero to more zero or more occurrence of any string. And positive closure is a variation of the same, which is indicated with L plus, which is a representation of one or more occurrence of the given string, right? So these are 4 operations. Along with that, other operations are also there. Let us look into an example of what exactly this operation means. So let us say, for example, that L is a set of letter, okay, which is indicated by A to Z and small a to Z. And D is a set of digit, which is indicated with 0 to 9. Okay. So if L and D are 2 separate languages, then what are the possible results if we perform the operations on these 2 language set? Okay, let us look into that. So what is L union D? So L union D is a set of letters and digit. That's it. Okay, so you put them together, it will become L union D. So LD or a concatenation is going to be a 520 strings of length 2. Okay, what is length string of length 2? String of length 2 is, like for example, you have taken one from L. Okay, L is A to Z, right? And small a to Z. And similarly, D is equal to 0 to 9. Right, so it is equal to 0 to 9. So you take 1 and combine. Okay, so LD means what? So one from L and one string from L and one string from D put together. That's it. So for example, I take A, okay, and I take 0 from D. So this is one of the string that is generated. Similarly, I will keep A, but I will take the second digit from L. Okay, it will become A1. Similarly, it can be A3. So like that, maybe Z9. Okay, or small a1, something like this. So it will go on until what? You get around 520 strings of length 2. Okay, each consisting of one letter followed by one digit. So this is what concatenation is. So what is L4? L to the power of 4. So is a set of all 4 letter strings. Okay, all 4 letter strings. Like for example, L is basically a collection of characters A to Z. So what you can do is you can simply take any characters, combine it 4 times. Okay, like for example, A is a string that belongs to L4. Okay, so 4 characters are there from the same set, which is L. Okay, or you can call also like have ABCD. This is also L4. Next is L star. L star is the set of all strings of letters, including epsilon, 0 or more occurrence, right? Similarly, what is L into L union D star? Obviously, this is the concatenation of L with L union D, 0 or more number of times. What is D plus? D plus is a set of all strings or one more, set of all strings of one or more digits. Okay, so this is how you can perform some operation on these languages. Now, performing these operations would actually give you the set of strings that particular language can actually have. Okay, now comes the part of regular expressions, which we were supposed to discuss about. So basically, this regular expressions provides us with ways to specify patterns that can be used to identify different strings of a particular language, right? So let us consider what exactly is a regular expression. So as you can observe here, the regular expressions are those which are built recursively out of smaller regular expressions using the rule that are described below. Okay, so what are the rules that we shall look into? So each regular expression denotes a language L of R, which is also defined recursively from the languages denoted by R's sub-expression. Okay, so we shall look into the rules first of framing the regular expression, and then we shall look into a few examples. So whenever you are forming a regular expression, these regular expressions are made using the following 2 rules, or they are basically formed using these 2 rules. First one is that epsilon is a regular expression and L of epsilon is epsilon. Okay, that is the language whose sole member is an empty string. Okay, so epsilon is a regular expression, and what it defines, the language it defines is nothing. because it's an empty string, right? So it's quite obvious that the language contains nothing. It is basically an empty set. Okay. Second rule, if A is a symbol in sigma, which is nothing but the alphabets, then A is a regular expression and L of A is equal to A, right? That is the language with one string of length 1 with A in its one position. So note that by convention, we use italics for symbols and boldface for their corresponding regular expression. Okay, so this is the notation that we normally use. But what second rule says is that if you have anything like a single alphabet, okay, like we have A. If we have A, what is the language, what is the string that is defined by A? It is, first of all, it is A. Okay, so language of A is nothing but A only, which is a string of length 1 and which has A, or basically it is identified using A, right? So this is what the second rule actually says. So epsilon and epsilon rule and the single alphabet rule you can consider. Okay, now using those rules and induction method, we can actually form different regular expressions. Okay, or basically we can define strings for different languages, right? So let us see what exactly they are. So what is R? And so when we write things in small letter, then that is basically regular expression, short for regular expression. Like for example, suppose R and S are regular expressions that are denoting languages L of R and L of S respectively, then following things can happen. Okay, so R concatenated with S is a regular expression which is denoting this particular language. Similarly, R into S, okay, is a regular expression denoting the language L of R concatenated with L of S. Okay, so I think union operation and concatenation operation. So R star is a regular expression denoting L of R star, and R, if we simply put, is a regular expression denoting L of R, right? So these are some of the things that we need to remember and how we actually frame a regular expression. So important point here is that you need to know how to write a regular expression. Okay, for a particular language, you need to know how to write a regular expression. I hope the screen is visible. Okay. So of course, the operators that we are using here, the star and the concatenation and pipe symbol, all of them, they do have associativity and precedence. Like unary operator has the highest precedence. Second is the concatenation, and third one is the pipe symbol, which is having the lowest precedence and is left associative. So or symbol, right? So how it is going to be evaluated, that is what has been mentioned here. So if you write something like this, then it actually means this. Okay, so this is one of the things. So let us now look into some examples of how we can frame a regular expression, or what exactly a regular expression means. Okay, suppose if we have an alphabet, just a second. Okay, suppose if we have a set of alphabet AB, the regular expression AB, if I write A bar B, what it denotes? Okay, if I have AB, A or B, what is the language that is identified by this particular regular expression? So it will either match A, okay, or it will match B, correct? Right? Not both together, either this or this. So the language that it denotes is A comma B. Okay, so check out the second one. What is the language that is defined by, what is that, A bar B, okay, concatenation, right, and A bar B. What is the possible language that is defined by this regular expression? Can anybody tell what is defined by this regular expression? Concatenation. So either A or B from this. So let me take A first. Okay. Then I will take again A from here. Okay, because it is A or B. So A is one of the string that is derived from this regular expression. So this will be a part of our language. I will keep A as it is, but instead of A, now let me write B. Okay. So this is also one more string that is derived from this regular expression. Now let me take B, okay, as common. Then from the second one, I will take A. Then let me keep B as constant. Then I will take another B from the second regular expression. So this is the language that is defined by this particular regular expression. Okay. Let's verify. Yes. So this is what the language that is defined. What is A star? A star means zero or more occurrences of A. We are already familiar with this. So including epsilon, we can have any number of A's, right? So what is A bar B whole star? So this basically denotes the set of string consisting of zero or more occurrences of A or B's. Okay, so like for example, the set has been defined here. I hope this is visible. You can follow my mouse cursor. I am unable to highlight it. So this is what the string that is defined by A or B star is. Okay. What about A or A star B? A or A star B. So either A, or it can be followed by B, or it can be preceded, or it can have a prefix of any number of A, zero or more occurrences of B. Okay. So this is what a regular expression can actually do. It can actually be helpful to derive certain strings of a particular language. Okay. Now this is a algebraic rule. I think you are familiar with this, all these commutative law, associative law, and all. So let us just briefly look into that. So law says that R bar S is equal to S bar R, which is obviously R symbol is commutative because both of them gives us the same set of strings. Similarly, R concatenated with S bar T is equal to R bar S concatenated with T. Okay, so R is basically associative. So concatenation is also associative. You can concatenate in different ways and you can still get a same set of strings. And concatenation distributes over R. Of course, you can verify this with a few examples. So epsilon, if you concatenate on both sides, doesn't have any effect. So it is identity property. R star is equal to R bar epsilon star. So epsilon is guaranteed in a closure. When I put star, obviously epsilon should be there. Okay. Then R double star is equal to R star. So means you can't have two stars. It is equivalent to one of it. Okay. R star is idempotent. So these are some of the laws, algebraic laws for regular expression. Okay. Now when you are writing a sequence of regular expression, it may get difficult for you to keep track of how exactly a regular expression has been formed, or maybe make use of them in your program or in your lexical analyzer. Okay, so there is a notational convenience that can be followed in order to give certain name to your regular expression, and these names that you give are called as regular definitions. Okay, means if you give some name to the regular expression, that is nothing but regular definition. Okay, so how do we define a name? For example, just check this out. What is A or B or C or up to Z and small a, B, C? All of these things are nothing but letter, right? So what we can do is we can give a name to it called as letter. Okay, so as I was talking about, we have A to Z and A to Z, right? So all of these things are nothing but letter. What is 0 to 9? 0 to 9 I can call them as digit. Okay, so now using these, if I want to form an identifier, then this would be the definition for an identifier. So it is letter follow and maybe an underscore if required, followed by a letter or digit. Okay, and this can be there any number of times. See, we have defined ID using the definition of other regular expression. So this is a regular definition. So letter is a regular definition, ID, letter underscore is a definition, digit is a definition, and ID is a regular definition. Okay. Now, similarly, just observe, there is one more regular definition that is given for an unsigned number. Okay. Now, this unsigned number can be an integer or a floating point number. So basically, it can be something like 5280 or 0.01234 or 6.6336 E4, or it can also be something like in exponent form 1.89 E to the power of minus 4. Okay, so all of these things should be matched by a common regular expression. So how do we write a regular expression for this? Okay, so first of all, what should be there to write? Just check this out. So first of all, I need, see what for example, if I take 5280, right, what it is made up of? It is made up of individual digits, correct, which is nothing but 0 to 9, right, which is nothing but 0 to 9. And if I want to match this entire thing, what I can do, I can simply write a, not I will write star, I will write plus. Okay, I can also write star, but I'll write okay, I'll write star only. Okay, so 0 to 9 star is going to match this. Okay, but now if I am looking for a number like 0.01234, right, then obviously there is two parts here. So one is on the left side of the dot and second one is on the right side of the dot. So what I can do, I can simply write this something like this. So I will write 0 to 9 plus, okay, because I cannot write dot and then I will not use this notation. Okay, so I will assume that before dot there should be something, at least 0 should be there. Okay, so 0 to 9 plus, then there should be a literal dot. Okay, then it can be followed by 0 to 9 plus, okay, or star. Okay, and how many dots can be there? For that also I can write a regular expression. Okay, so but this will not match this one, which is 6.336 E4, correct? So this is one of the problem. So I need to add E also. So then even if I write a regular expression for this, it may not match 1.89 E minus 4. Okay, what is the difference here from this one and this one? So here E was there, but plus 4 was there. Here E is there, but minus 4 is there. So all these things needs to be put together. So what we will do is, we will write individual regular expressions, give some name to them, and then use those names or definitions in order to frame the entire definition for our number, which is an unsigned number. Okay, so how we are writing it, let us just look into here. So first we will identify what is a digit, because every unsigned number is made up of digits, correct? So what is a digit? Digit is anything from 0 to 9. Okay, either I can write it like this, or I can also write in using character class, which is something like this. Okay, this is totally up to you. So you can write it like this, 0 to 9. Okay, so this is one thing. Then this is a digit. Okay, so you can write it as a digit. So this will match what? This will either match 0 or 1 or 2, something like this. But if I want to make it as the first one, which is 5280, okay, if I want to match this, then I need digits. Okay, so what is a digit? If digit is 0 to 9, what is digits? So it is something that is at least 1 followed by any number of digits. Okay, so followed by any number of digits means it can be 0 to 0 or more occurrence. So digit into or digit concatenated with another digit star. Okay, now let us talk about fraction. Okay, so may be there, may not be there. So we will give it as optional fraction. So what is optional fraction? It should be dot. There should be dot at the beginning. Then it can be followed by any number of digits. Okay, or it may not be there also. Okay, like for example, if I write 27, then there is no dot here. So obviously this particular part is not present. Okay, so this is what optional fraction part is. Now let us check optional exponent. Okay, so exponent means e part. So how we can write an regular expression for that? E, it should be e. Then e should be followed by either plus or minus. Okay, it may be there or may not be there. Okay, like for example, I can write e plus 4, right? Or I can write e minus 4. Okay, or I can write e4 also, like as it has been written in the third case here. But that has to be followed by some digits. Okay, so we'll write that. Then the last one is number. Last one is number. The number is it's a combination of all of this. Right? So you can observe here, it's a combination of all of it. So what is it? It's digits followed by optional fraction followed by optional exponent, right? So that's what makes it a number. Now all of these things that we have given some name to these regular expressions, all of these things are regular definitions. Okay, so this is what a regular definition is. There are few more concepts related with this. And then we shall finally go into how regular expressions are actually programmed, or how programs are actually made out of regular expressions. Right? We will do that in the next session. Let me take the attendance. Taken the attendance. So we shall look into the other concepts in the next session. Okay? So if I do have any doubts, then do let me know. I'll share the attendance sheet with you. So do fill that up as well. Okay. Thank you, students.